So let me welcome everyone to our CAWASA webinar. We like to welcome everyone back after quite an absence. I think since October we haven't met. And so we hope to be back and running every Wednesday with the support of Operators Without Borders, Valerie Jenkinson, the chair of Operators Without Borders. We'd like to thank them again for always finding us some very good speakers. And we do have um, today, we have a pretty interesting topic. Water treatment by ultraviolet light, viable in low resource settings. And this is going to be presented by Dr. Onkundi Nyangarasi. I think you're from Kenya. And so I would like to welcome all our colleagues from the water utilities around the Caribbean region. And some of you who are joining us for the first time outside of the region, I think we have Mr. Hugo Rancharan out of Belize Water Services. And I think he may have a couple more of his staff on board with us. So we would like to welcome all of you and wish everyone a very productive 2025. I should also let you know that this year we have some exciting times ahead of us. It's the year of our conference. It's going to be held in St. Vincent on from June 25th to the 27th, so you can begin checking your calendars for that. And we'd really look forward to having some of you there in person. So let's get now to Dr. Nyangarasi. The floor is yours. Please proceed.
Yeah, thank you so much. Yeah, thank you. You have tried to pronounce my name. It's Nyangarasi. That's my surname. Yeah. So my name is Dr. Paul Onkundi Nyangarasi. Thank you so much. Maybe before I start, I'd like maybe to try and share my presentation, then we can start from there maybe. Are you able to see my presentation?
Yes,
Maybe.
I'm seeing your screen. I think you go there.
Okay, yeah. Yeah, thank you so much. I'm Dr. Paul Onkuni Nyangaresi. So if you see on the screen, there's another name, which is Dr. Sarah Beck. I like in my presentation to recognize her, and luckily I've seen her in today's webinar. She's my supervisor, and we have really worked together for the past 3.5 years here in the University of British Columbia, Canada. And she has been really supportive a lot. That's why in all my presentation, I really have to acknowledge her and her efforts in what she has done to me. Yeah. She is the one who really helped me to come this side, and then we are working together in her lab. So more I'll talk through while doing the presentation so that we don't waste a lot of time. So the topic of today is really water treatment by UV viable in low resource settings. We really need to understand because we are moving into an era of technology. So, and we have now these technologies with us, that is ultraviolet light. And then we are asking, is it really viable in rural communities, underserved communities, remote communities, marginalized communities? Is it viable? Can we apply it there? And therefore, today I'm going to give briefly a brief introduction what ultraviolet is. Some people here may know about it, but I'm not going to go into details. I'll talk just on the basics, and then I'll give a case study where we have applied the UV system. Uh, on this slide, when you look at it, you realize there is a blue color and then like orange. So you need to ask yourself where your country is, and then you check whether you can just have clean water from a tap or not. So if I look at my country, that's in Kenya, it's not easy to get a clean water from a tap to drink. Wherever you walk around, it's hard. But here in Canada, I can go into a building, I get water from the tap, and I can drink, something like that. So there's something which we are really asking ourselves. Is it possible for many countries to have water in a tap? And what are the things which can happen for those countries to get, like in Canada, in the United States, in Australia? And what are the challenges these people or these communities or these countries are facing? So the introduction of this presentation, one, the issue where we are looking at this, where we need to where we are interested in applying ultraviolet light. The basic is about water. But the challenge is, what is this about water? We realize that so many people, including children, die from waterborne diseases. There's so many of these diseases, including dysentery, cholera, typhoid, and many more. And these diseases are normally caused by waterborne microorganisms, which include bacteria, virus, and protozoa. So I've given some of the examples. All of you normally come across or you know about. So, and one of the key thing is the Sustainable Development Goals, that's goal 6. The key is we need to ensure availability and sustainable management of water and sanitation for all. Like some have achieved this, but some have not. That is why I'm targeting the low resource settings. And therefore, that is why there's need really to bring or to provide clean drinking water for everyone, even if some few countries or some few locations have this, but some of the countries have not, and particularly in the low resource settings. So what do we call water disinfection when we are talking about the water disinfection? So water disinfection here is removal or destruction of harmful pathogens. And this can also occur at the point of use, whereby you are collecting water and using at that given point, you can do disinfection, or at the point of entry. So I'm giving a diagram, a symbol diagram of water treatment, but the focus here is just on disinfection. That is the one which I'm focusing more, because we know in water treatment, there's so many stages. Maybe wastewater treatment, there's coagulation, there's flocculation, sedimentation, but the interest more is on disinfection. And there is different ways you can do the disinfection. Either you can use chemicals, or you can use heat, or you can use ultraviolet light. So, and at the point of use, this is where we are coming. The ultraviolet, basically, most of it is used sometimes in the houses. So in these houses, that's where we have like the point of use. So in chemicals, what are the problems which are associated with chemicals? If we start, because we have the different types of treatment, chemicals, and then UV, maybe heat, and this heat through boiling. But what are the challenges that we face when we are using chemicals? For example, chlorine, or we are using ozone. So what are the challenges we have? One, there's the chlorine itself can lead to introduction of disinfection resistant to bacteria. And then the other one is chlorine, you know, it has so many issues concerning the taste and the production of very bad odor. And some communities, particularly in these low resource settings, they don't like the taste of chlorine. They don't like the smell of chlorine. So if they don't like this, so what do we need to do to treat their water, considering they're using contaminated water? And also, the other challenge of the chlorine is it can produce the disinfection byproducts. And these disinfection byproducts, they are they can cause some different types of cancer. They can cause some mutations in some of the microorganisms. And then also they can affect the reproductive system of human beings. So these are some of the challenges. So although we have these challenges, we are still using chlorine. And why are we using? It's because we have not really gotten a very simple method or a very simple means of treating or disinfecting water, which is acceptable globally, including the marginalized or the low resource settings. So what about the boiling then? If we say there's challenges with the chlorine, so what about the boiling? So the boiling, it also lacks the disinfection residue, and is time and energy consumptive. And then the other thing is when you use firewood, it can lead to pollution. You can see a lot of smoke there. It's everywhere, especially in the low resource setting. They have this challenge, lots of smoke produced. And all these are associated with some of the diseases, respiratory diseases. Also, it can include cancer. So these are the challenges which we face. Particularly, I'm looking in the low resource settings when they are using the firewood. And then boiling also can lead to degradation or deforestation or greenhouse gas emissions. And then one main challenge also is about the burden which the women, the girls, and the children they face when they are going to collect the firewood. As I come also from those raw resource settings, I have seen maybe very young girls going to collect the firewood. Sometimes they get abused in the forests when they are collecting the firewood. And also at home, even the children will be abused, like they are beaten, they did not go to collect the firewood. So these are the challenges. The abuse does not only occur in the forest, but also it occurs in our homes because the parents, they have to push the kids to go and collect the firewood. And then if they did not collect enough firewood, they are beaten. So these are the kind of abuse which I'm talking about. And I've grown through this, so I know what these children go through. And I have to bring this concern. Sometimes we say it's a burden for women and children and girls. We forget boys. I remember I was a little boy and I used to collect the water. I used to go to the forest to collect firewood. So boys, young boys, alcohol. And again, boys face a very big challenge, especially when they go to collect the firewood. When they find the girls start to laugh at them like this, not their responsibility to collect the firewood. So the boys you find, they come from a home, they are only boys. So if they are only boys, they have to go to fetch water, they have to go to fetch the firewood. So when they go to fetch water or firewood, now the girls start laughing at them. So they get also, it's the abuse, it cuts across. Yes. So what about now the ultraviolet irradiation? So UV is a disinfection, and this disinfection irradiation is a physical process. And we have so many advantages of ultraviolet irradiation. One of the advantages is it does not produce the disinfection byproducts, which we saw being produced by the chemicals, and then does not alter the water quality or the taste or smell. So UV never changes the taste of water, never changes the taste. So it's not really that expensive, but this when we are going to look as I proceed with the presentation to see like, is really UV expensive or not? And then is easy to operate. The moment you have a UV system, you just install, you're done. So you don't need to do, and the only thing you can do is maybe to check later. So then there's no chemicals which are needed. You don't need to add any chemical. There's no chemical product, like that's how UV works. And then the disinfection is very fast. It's just within seconds. I've done so many experiments. I've come to realize just within seconds, whereas the chlorine requires some time for it to be reactive. And then also it never produces or disinfection resistant to bacteria. So, but what are the disadvantages of these UVs? And then one of the disadvantages is it does not have a residue disinfection capacity, meaning if the water has passed through the UV system, you need to use the water immediately. Otherwise, if you store it, then microbial can start to grow again, which is now a good thing for chlorine. When you're using chlorine, there is that disinfection residue. But for UV, it does not have. And then it's not possible to continuously monitor the amount of energy the UV system. But I've put a star there because of the new technologies which are coming up. There's sensors which are coming up. So again, you can easily monitor. So it's UV is still in product or in progress. Therefore, you can have sensors still, you can put the UV system to monitor this. And also danger of mercury. There is two types of UV systems. I'll explain that one later. So one of the UV system can produce mercury, which is not good for the environment, but another one does not. So I'll explain that one later. So also the UV, one of the challenges it has is it requires electricity, which is not the same as like chlorine. Chlorine, you don't need the electricity, but the UV, you need electricity. And therefore now that forces us to go back to our topic, which we are saying like, is it really viable to low resource settings? And considering these low resource settings, they don't have enough electricity, and the one which is there is expensive, and sometimes it's not there, it's not continuous. So can really use UV in those low resource settings. There is so broad applications of UV. But now today we are specifically looking at water disinfection. And in this UV, one will really, we are talking about UV. So what is this really UV and what's the wavelengths of this UV? So when we have a spectrum of light, light always, you can have wavelengths from 100 all the way to even 1200, but normally we go up to around 800. So visible light, like the blue, green, red, all of those, visible one, they range between 400 to around 800 or 780. But now the UV light, it's just within 100 to 400. So, but the one which is optimum, which most microorganisms absorb, the peak is around 265 nanometers. That's the peak. But there's so many wavelengths around that, which I'm going to discuss later in this presentation. There is, when we are doing UV disinfection or applying UV in water treatment, we need to understand how this UV, because I've mentioned like 265 nanometers is the one which most microorganisms absorb. And now what is this that is absorbing this light? So what are we targeting? So what we target in a microorganism is DNA of a microorganism or the proteins of the microorganism. Remember, the moment you affect or you inactivate the DNA of a microorganism, then it will not be able to reproduce. And also, if you destroy the proteins, then it means if you have affected or you have destroyed the microorganism and also the microorganism itself through the destruction or inactivation of its DNA, then also you have affected the proteins. Proteins are responsible to ensure there's curing taking place. So also if you destroy the proteins of that microorganism, it means that microorganism at the end is not going to perform its functions, and therefore it cannot cause any infection in a human body. And there's different wavelengths which are in this UV light. So we have the 254. The reason why I've mentioned the 254 is because of some UV systems which emit light along the 254. So this along where the DNA and the proteins absorb the 254 nanometers. And then the other one is the 265, and you can see where the DNA and the proteins, where it is absorbed. This is the spectrum of that. And then we have another one is the 280. You can see where it is absorbed. And the latest which people are now talking about is the 222 nanometers. So I'll discuss more as we move down on this. So these are some of the specific wavelengths which are very critical in disinfection applications. Either it can be in water, in service, or in air disinfection. So these wavelengths which I've listed here, and you have seen where they are absorbed, they are so critical in disinfection applications. So in UV...
Well, I just wonder, are we supposed to be seeing a PowerPoint? We're only seeing you at this point.
Oh, you're seeing me at this point?
I see a
Yes.
PowerPoint. I see a PowerPoint.
You do?
Yeah.
Yeah, too.
Oh, that's
So are you
interesting.
seeing all my...
I'm seeing Paul's very smiling face on my screen. Sorry, if everybody else is seeing it, that's fine.
So the rest are seeing my presentation.
Paul, proceed. The presentation is going fine.
Okay.
It's on the
Thank you
screen.
so much. Okay, so you are able to see my PPT, okay?
Yes, apparently it's just me at my end. So go ahead. Sorry.
Okay, thank you so much. Yeah. So I was explaining about the wavelengths. So I've mentioned the 222 nanometers, the 254 nanometers, 265, and the 280 nanometers. So here I'm looking at how is this UV affecting now the DNA or an RNA of the microorganism. So before microorganisms are exposed to UV light, this is what happens. So you can see here the DNA, here it is a double strand, the RNA is a single strand. So after you're going to expose the DNA or that microorganism with the UV light, what happens? Some of the strands are broken down. So this is what is happening. And then there is some of the microorganism, there's what we call the pyrimidine dimers, PD, in the growing cells. And then we have the spore photoproduct, SP, is what is formed, and then it affects within that strand of that DNA or RNA. And therefore, when you are affecting the DNA or RNA of a microorganism, now you are affecting its performance or it's not able to reproduce. So one of the challenges of some microorganisms, especially bacteria like E. coli, when they are exposed to UV light, they can again repair themselves if they receive some of the light. And that light is always more than 300 nanometers. So the reason why some of the microorganisms are able to repair themselves is because they have some enzymes which protect themselves. It's like our human beings. You have some white blood cells which can, like, when you are sick, they can fight to kill all that. So the same applies to microorganisms. They have enzymes. So the moment they have been affected, the enzymes can come and then circle this pyrimidine dimer around here so that they can receive. So for these enzymes, for them to start to work, they must be activated by light. And that light should be more than 300 nanometers. So when they surround that, then they are able to remove that pyrimidine dimer, and then the DNA is set free. Again, the microorganism goes back to its normal and then start to perform its function. So this is one of the challenges that we need to understand. Like, if UV, again, some microorganism, when they are exposed to it, they can repair themselves. So what do we need to do? So is it really UV effective in inactivating microorganisms or not? So those are the challenges which we need to look into. So now I go back to UV sources, which all of us know: the sunlight, UV mercury lamps, UV light emitting diode, and excimer lamps. So the sunlight, we already understand that it has been applied so many years in water treatment, in low resource settings. We have seen all that. But one of the challenges of the sunlight is it is unreliable for some communities or some countries whereby it is cold seasons. Yeah. So, and also another challenge is only 10% of the UV light from the sun is the one which is able to penetrate through the atmosphere to reach the ground. And this only is the UVA. I'll later on explain this UVA, what it is, but only 10% which penetrates, and therefore all the other one is absorbed. So the good UV, which is normally can be applied in disinfection, is absorbed, so does not reach on the ground. So mercury lamps are some of the common, they're very common, they're used widely. So, and this, some of them like that. And the challenge with the mercury lamps is there's two types of them. Some produce, they emit light at 254 nanometers. These are low pressure lamps. And then another one is medium pressure lamp, which emits at 200 to around 400 nanometers. So this is the spectrum of the mercury lamps. And if you see, this is the 254. And I already showed you earlier where the spectrum under which the microorganism absorbs, so where the 254 is absorbed. So the reason why I'd shown you that slide earlier of the 254 is because we have mercury lamps which emits UV around the 254 nanometers, and they're widely used. So, but we are looking at ways in which we need to eliminate this, but I'll show you the challenges of UV mercury lamps later. So the other thing is about the UV LEDs. So UV LEDs can emit different wavelengths. Now you can see we have three types of them. That's the UVC, which is 200 to 280, UVB, which is 280 to 315, and then UVA is 315 to 400 nanometers. You can see now UVA, this is 315 to 400, is the one which we can get from the sun, only the 10%. So then we have these other three remaining, UVC and then the UVB. So what are these really UV LEDs? For us to understand UV, and we're talking about UV LEDs, we need to understand the background of that. So a UV LED is a PN junction solid state. When you apply current, it can be able to produce light. So this is a simple junction of LED. And inside a UV LED, it has a feature like this. This is just a basic I've given. There's so many complicated ones, but I've given just the basic. And one main thing in the UV LEDs is what we call the active region. This active region is the one which produces light. And this active region is made of some of the chemicals which we call aluminum gallium nitride. And what happens for you to be able to change the wavelengths of these UV LEDs, what you do, you change the amount of aluminum in gallium nitride. So when you keep changing that amount of aluminum in the gallium nitride, you are changing the wavelength. So the more you are putting aluminum, the lower the wavelength you get. But the challenge again comes, the more aluminum you add, the more you destroy the material. So the material quality is destroyed. It becomes very poor. That is why it is hard for now to get UV LEDs of very low wavelength, like of 200 nanometers, 250 nanometers, or 220 nanometers is very hard to get because of poor material quality, which we cannot get when we are adding the aluminum. Also, when you have less of the aluminum, it means you have longer wavelength. That's why nowadays, everywhere in the market, you can find wavelength, which LEDs which are emitting at UVA, and they're very cheap because you don't need to put a lot of aluminum and the material quality is very good. So those are some of the challenges and how the UV LEDs are fabricated. And one will ask why we don't have so many UV LEDs in the market. This is the main challenge that people are facing now, but with improved technologies, I hope people will come out with very good UV LEDs. So these are some, after LEDs have been made like this, then they need to be packaged. There are different ways they are packaged. And one of the main we have is SMD 5050. This is the one which is commonly used in disinfection systems, the water treatment systems. For example, when you have that, you can design a printed circuit board, and then you solder the UV LEDs, an example you can see here in these pictures. And then from there, after you have done that, you can test. This is the system for testing the power of the UV LEDs, the radiance of the UV LEDs. After you have tested, then you know how much this LED is able to produce, what wavelength is this LED able to emit, and then from there, you can make the UV system. That's why you see now in the market, we have different types of UV system, like in North America, we have these types. These are very common nowadays, and some have applied this system in water treatment. So what about the excimer lamps? This is now the latest technology. I mentioned about the 222 nanometers. It's also latest. It's coming up, and people are trying to use the excimer lamps in service and air disinfection. Because of these 222 nanometers, it cannot be able to penetrate through the skin so deeply. It can be absorbed on the surface of the skin. So I don't want to go too much on that because we want to concentrate more on water treatment. So now, we have talked about UV systems. We have talked about two main types of UV emitting systems. That is the UV LEDs and UV mercury lamps. So why or what's the difference between these two? So you can see here on the UV LEDs, UV LEDs can be able to give you different wavelength that you want. If they're able to fabricate, you can get UV wavelength at the UVC, and then you can get at the UVB, you can get the UVA. But the challenge for the mercury lamps, it is fixed, so you cannot change. For low pressure, it's still 254. For the medium pressure, it emits within 200 to 400. So it's just fixed. Then the UV LEDs, they're environmentally friendly. They don't have mercury, but the mercury lamps, they have mercury. And then the UV LEDs are durable, but the mercury lamps, they can break easily. They're not durable. And the UV LEDs are very compact. I've shown you a picture of that. And then the faster startup. If you have a mercury lamp and a UV LEDs, then you turn them on. The mercury lamp takes some few seconds or minutes for it to start up to maximum energy. But the UV LED, it turns on immediately. It's just instant. And therefore, also the UV LEDs, they have a potential of consuming less energy. When you compare the two, UV LEDs, they're like 80% energy efficient as compared to the mercury lamps. So for the UV LEDs also, they have a potential of longer lifetime as compared to the mercury lamps. And also the UV LEDs, you can turn them on and off very fast without having or damaging them. But the mercury lamps, you cannot. So these are the differences between the two. Now, up to this given point, if someone has a question, you can ask, or if I can continue to proceed so that I can now explain or give a case study where we applied now the UV LEDs. And the reason why we applied the UV LEDs is because of those disadvantages of mercury lamps And then we said, okay, UV LEDs is a new and emerging technology which is coming up, and we see it has the potential to replace the mercury lamps. And therefore we said, let us take these UV LEDs and test them in the low resource settings. So I've given you a world map, and this now you can see also where your country is, and you can see where Kenya is. That's where we did our test. And then Kisii, that's a community where I come from. It's very far from Nairobi. And then from Kisii, now I live also far from Kisii town. So deeper, which is around 40 kilometers from Kisii to in a community which we call Nyamesocho. So this is a community where I live. And this community, you can see where the river is in that community on that. So the main water sources in Nyamesocho are just surface water. We have stream, and then we have protected spring, and then we have a borehole, we have rainwater. So these are, you can see the main water sources that we have in our community. We don't have piped water from the government or community piped water. We don't have, we depend on these sources of water. So then the challenge is, how can we treat this water, or how can we use this? So if you can see, even there's so many worms. When we collect rainwater, you can see live worms, many of them. So this is the water we use in those communities. And that is why my topic was looking into water or application of UV LEDs in low resource settings. So I could give you also another picture of a school which I went to visit. So you can see how also they collect their water. So there is no piped water from the government. So they collect water also from the roof. But this water which we have here in this school is a mixture of rainwater and also borehole water. But the water, they put chlorine inside. So there's a very big challenge of like, okay, what if this chlorine is producing pipe product? What are the dangers it will cause to the student of the school? And this school holds around over 2,000 students. So what can happen? So we went there to see how can we bring in the UV LEDs to incorporate into this system so that we can treat the water for the students. So before I started on the project which we did, I went home to do a pilot project, and this was just for rainwater. And therefore I designed, you can see collecting the rainwater, I put the tanks in the roofs, and then I had a very small UV system, which we got from this one company in the USA. So it is the flow rate of this system was 2 liters per minute. So I only tested this system just at home. So I wanted to see how it can be able to perform. So the results I got from this was like this. So in what at the test, I took some of the samples from the stream, spring, borehole, rainwater, and then piped water. You can see there were so many bacteria in most of the water which we collect. That is the E. coli. And therefore, after treating it with the UV light, this is what I was able to get. So you can see there's a lot of good results which I got here from the tank. You can see inside the tank, this was before UV. There's still E. coli, which we found. But after treatment, we can see there was no microorganism which was found. So from this, we saw like, oh, then this UV can really be beneficial or can be applied. But one of the issue which we encountered is, before I go on the issue, I had to test the UV because UV transmittance, because for UV light to be applicable, you must have clear water. It means you must remove some of the particles, you must move some of the big microorganisms so that the water is clear. So the UV performs so well when the water is very clear, the UVT is very high. It's the same with the chlorine. Remember, chlorine also, you cannot add chlorine where the water has so many particles. So the efficiency of the chlorine will not be effective. So it will be lowered. And therefore, chlorine and UV are the same in terms of requiring a pre-treatment. That is, you have to do filtration before you apply the UV light or before you apply the chlorine. That is the same across. And therefore, when we did the filtration using the biosand, so this is what we obtained. The UVT was so high, and therefore that's why we were able to obtain very good results in terms of disinfection. So this is what we had in terms of after filtration, after biosand, and we had included also charcoal, you can see the UVT was so high, about 95%, which is very perfect for applying the UV system. Now, these are the challenges we face when I apply that small system. One is frequent power outages. I told you in the rural areas or low resource settings, we don't have continuous electricity. We don't have enough electricity, and the one which is available is too expensive. So the one which we don't have, it's not continuous. So we used to have frequent power outages. So we had to get some challenges when we are using the UV system. And then the other thing is the UV system which we use. It had a very low flow rate, 2 liters per minute. This is not enough for a good number. Like if you need more than 50 people, 2 liters per minute, and they need to use the water for drinking, the water for cooking, and other things. So this system was not good at all. And for other thing is this community does not have resources for scaling up the system, and therefore it's a challenge for that. And therefore we were not able to proceed far with this given system. But we continue to think on how we can do with a very high and powerful UV system. And then that brought us to another system which we started to do a project on. And this now project which we did was in a school, and this was also rain harvesting and treatment using also a UV system. And this was implemented in a school called Genyabayo, and it was funded by MyTax here in Canada. And this was in collaboration with two companies, that is MW Technologies and Clear, and together with my supervisor, Dr. Sarah Beck. So this is where the school is. This is the school location, and this is what we have. The school is here, you can see on that slide. And then when you move down, you see where the students who are going to collect the water is around 500 meters to the forest. That's where they get the water from. And this water, remember, is from a protected spring. This spring is contaminated. And then here in this protected spring, we have a river. So the student collect the water from the spring or from the river, which all of them are contaminated. So this is the picture of the school which we did the project. And the school had around 363 pupils and 19 teachers and 3 non-teaching staff. So what we did here, you can see how the students collect the water from the protected spring, and you can see how they carry their water, and this is how they do their cooking. So this is the system which we were able to build, and this system, it contains around 4 steps. One, there is rainwater harvesting. And then after rainwater harvesting, we have a tank, and this tank is 10,000 liters. And then from there, we have a pump, and this pump will pump the water up to the filtration system. So the first tank, the tank which is here labeled number 2, is biosand filtration, just sand, only sand to remove all the particles. And then after that, the water here is controlled automatic. So the system is automated. And then the water flows to the another tank, which is tank 3. This tank 3 is for holding the filtered water. And then from there, this water now flows through the UV system. This is the UV LED here for final disinfection. Then it is collected through the taps. So this is the really picture of what we did in that school. So, and then you can see the system which we installed. It was a very big system. It has around 8 GPM. That is around 35 liters per minute. And we were able to produce a very good quality. So this is the test. And in this system, we had 8 taps. 2 taps were for the kitchen. And then we had other taps, which are around 6 for the children. And we were able to produce very good quality water for that given school after doing the testing. And then this is the engaging with the parents and the student. Here we were doing the survey, questionnaire, filling the survey. And this is the quality of water which we obtained. In the months which we tested, you can see before the water in the stream, the borehole, protected spring, and the harvested, all of them, they were contaminated. In fact, too much contamination with the E. coli. But we took another sample for conversion, which was for chlorine treated water, which did not have any microorganism. But all the water which was being used by the student in the school, the water in that community is contaminated. And then after treating the water, this is what we obtained. After Harvesting, still the water was contaminated, that is in the big tank. And then after filtration, the microorganism reduced. People use biosand filtration, but still it's not 100% efficient. That is why we were able to see the microorganism still. And then, but after UV treatment, we were able to find no microorganism after UV. Luckily, with this system, the water is not stored. The water is used immediately after UV disinfection. So after we asked a questionnaire from parents and the people who were around, so we were able to find very good results. So they were able to say the system, it was very excellent, around 95%. Now, what were the outcomes of that system which we implemented in that school? So one thing is we were able to harvest, like during the rain season, we were able to harvest 10,000 liters of water, and the system can be able to treat around 500 liters. This 500 liters is used per day, but we can be able to treat more water. So this one was dependent on the usage. So if the students are many, it means we can be able still to produce more water. So the other thing is this water, if it is a dry season and we have collected 10,000 liters, this water can last for 20 days. So meaning the likely part is in the community there is enough rainfall. We only have dry seasons like 1 month or so, but even within months still we can get short rain. So we don't have a challenge of collecting the rainwater because the area is having a lot of rainfall. And then this project was really funded, and we were awarded an award with my tax. That is how now I was able to meet Valerie, and then I'm able to do this presentation today. So the next project which we are planning now is to think on how to install a system which can be able to disinfect water for the community. The one which we looked for was rainwater harvesting for a school, but the rainwater, that water cannot be used for the community. The community, they are dependent on either the river, they're dependent on either maybe protected spring. So we are thinking, how can we implement the similar system, but for a protected spring? So this is the protected spring where the community, over 1,000 people, collect the water from here. You can see the flow rate is very low. And this, after we tested this water, the quality was very poor. This is how the people collect the water. You can see young children, girls, and they're sitting there because they'll spend even 1 hour, 2 hours waiting for water to collect. So how can we solve this problem in these low resource settings? So you can see the quality of that water is very poor. This is full of E. coli. So we need to see how we can solve this. And solving this, we are intending to produce or to bring in the new technology, that is the UV LEDs. And that question, we go back to our topic, is UV LEDs viable in these communities? And therefore, in this given point, water sources in this community is very poor, and there is also very difficult access during the rainy seasons. And also another thing, the UVT, which I said is so crucial for UV disinfection. The stability of the UVT, the stability is very high, meaning the UVT is very low. And there's color change and bad smell during the rain season. So how can we solve this problem for this community? And then the other thing is the flow rate reduces drastically during the dry season, as you saw in that diagram which I showed you. And then the other thing is the water is highly contaminated with microorganisms, and the people normally have so many illnesses, and the hospitals are very far. So how can we resolve this to help the people? And also another thing is to reduce the burden to women, girls, boys, and children fetching water, which are also prone to abuse. So these are our key aims in doing all this. And one major problem is these people, they're not connected to electricity, most of them. And those who are connected, the electricity is not continuous, and again, it's expensive. So how can we look at all these things so that we can be able to solve the problem for that given community? And then the other issue is there's no to minimum government services. This community receives like very minimal. Nobody cares about the water they drink. So it is the community which needs to come together to see how they can have their own water. So how can we come in to help them? And therefore, in this given case, this is the other issue. The medical facility is very far, and there's very poor road network. and people don't have even cars. So this is the system also we have proposed to do in that given. We are thinking about it on how we are going to implement. It's the same, but now here it's not about the rainwater, but we want to look at the protected spring and see how we can redesign this. So there's lots of engineering to go around here. Then we continue. Then finally we apply the UV LED system. So what are the potential outcomes in this is we are intending to provide around clean water to around approximately 1,000 people. And then we need to improve the sanitation of that given area. And then at the end, we'll be able to improve or reduce the burden of waterborne diseases and also reduce the burden of women and children collecting the water. And most importantly, we need to adapt to climate change because during the dry season, the flow rate of that stream or that protected spring reduces. And also even during the rain season, the water quality really goes very low. The color increases. There's a very bad smell from the water. So how can we also look at these challenges and be able to solve this kind of problem? So this is the photos of what happens in that community. And therefore, this is our picture from our group here in the University of British Columbia. And some of them have graduated, some of them have finished. So we have few now remaining. And I really thank you. That is my presentation that I had for today. And therefore, I'll be able to ask for questions if there is. Thank you so much.
Thank you so much, Dr. Paul. That was really a fabulous presentation and quite a bit of thank you for sharing your scientific findings. And I think that must be a lot of your work. And I know that you said your supervisor is monitoring your presentation as well. So I thank you for sharing that with us and the many challenges. I think I think the audience is here and they may have questions for you and some of the observations as well. I know.
May I, Ignatius, just say that it wasn't mentioned at first, but Paul, in 2024, he earned the MITEX Innovation Award in the Inclusive Innovator of the Year category. It's an honor that recognizes achievements that promote social inclusion, incorporates diverse perspectives, and prioritizes accessibility. So that was one of the reasons that I first was brought to the attention of the work that Paul does, because this is a very prestigious award that he has won for this technology that he's put in place.
All right. And I think there are some of our participants here who may have, you did posit a few questions, and we may have some ideas for some of our operators who work in different systems, particularly with filtration. You did mention about the lack of electricity in some of these communities. Did you explore any of the possibilities using to power these systems using photovoltaic systems, small solar panels, as it were?
Yeah, thank you so much for that. I do not go so much into details for that, but one key thing is the system which we install is about the PV photovoltaic system. So the school doesn't have continuous electricity, so we were using the solar system, and that is what we are exploring more. And we have realized the solar system is cheaper than the grid, the electricity which we have, and is so efficient in the system which we install. So we incorporated that, and always in our project, that is what we are interested in. Mostly when we apply that solar system, because the UV system requires very minimum amount of energy, so the remaining now they use for lighting. Yeah.
Excellent.
Thank you so much.
Colleagues, the floor is yours. Should you have any questions or comments, please proceed.
Yes, Paul, from my experience in Kenya right now, electricity is about 50 cents per kilowatt hour. And here it's an average maybe of 20. So in spite of the economic difference where they're only making maybe $5 a day in their salary, they're paying more than twice as much for electricity to solar panel, okay, right now.
Yeah, sure, Father Ken. Thank you so much, and thank you for attending the presentation. I appreciate. I met you, and thank you, Valerie, in the meeting which we had. I'm so grateful on that. So I'm happy Father Ken has worked in Kenya, and he has seen all this. The electricity in that country is very expensive, as if compared to here. Considering the people even earn less than $5. In fact, $5 is even a lot. Others spend a whole day. There's nothing like they don't earn. So they're only working for the food. But when you tell them you need to pay electricity now, they get stressed about it. They don't have money now to pay the electricity, whereas they're looking for the food. Yeah, so that's where we are thinking on like, because it's expensive and again, it's not continuous, the solar system is the best option for them as compared to the other. Yeah.
Right. You also mentioned about your filtration systems. And I know in some of these parts, because I saw that you indicated the young men have to go fetching firewood for cooking. But so I would imagine there'd be quite a bit of charcoal that is being made. What about some of those options for filtration?
Oh, wow, that's amazing. Thank you. Thank you for that. Yeah. As I mentioned, and I think we are aware also about either chlorine or UV, there must be filtration. You cannot add chlorine without filtration. So that is like common through. Same UV, you can't do UV without filtration. The light cannot penetrate through. So one thing we do is biosand filtration system. And one of the system which I did the pilot study which I did at home, I had two. That is the biosand and then the charcoal. So I included the two of them. So, but the school for now it's running. So we wanted to see a whole year how the biosand system is working. And then we go again, we add the charcoal. We see also this efficiency because also we want to test this UV system, how this performance is. Before the UV system, still you can use only the biosand filtration and the charcoal without even the UV. Like my home, that's what I designed, biosand filtration system, and then I added charcoal, and then we don't have the microorganisms. So the only challenge with the charcoal is you need to keep on changing. So we are planning on how to do a long-term experiment to know like so that we can enlighten the community. We have included the charcoal by when are they supposed to change so that it can perform its functions properly. So also the other thing which you have mentioned about the boys, young boys and young girls, when I was young, we were taxed. We're going to fetch firewood, collect water. The challenges I remember we used to face now, us as boys, is the girls, they have to mock us, they even abuse like, boys, you don't need to come here. You're not the one supposed to collect water. It is girls, like that kind of thing. So like now the boys end up being shy. And when they go home, the parents will not know that they have been like really ambushed or scolded by the girls. For them, they'll be beaten. Why did you not collect firewood? Why did you not say the girls chased me? You cannot say that. So the abuse is both girls, boys, yeah, and then over women, and then the just children. So it cuts across that. And also, even nowadays, like even when I go home, because I know we use firewood, I will not like allow my mother to go and collect the firewood. Like I'm the one responsible to go to the forest, cut the firewood, then bring home. So like it's a shared responsibility which cuts across. Like that's how it has changed all these times. Although a long time ago, yes, only women and children and wherever young boys and girls used to go. But nowadays, it has really changed. You find like the men, they go to the forest, they cut the trees wherever, they collect everything, then the women and girls, then they come to college. So it has become like a shared responsibility. So still it's a challenge. We may not solve it now in terms of using firewood, but as time goes, these things will really change. But as per now, that thing is going on, but we can still solve what we are able to solve, especially now in the water. Yeah.
We have a question in the chat from Mr. Rancharan of Belize Water Services, and he asks, will the success of the pilot project be expanded further from the community level?
Yeah, sure. Thank you so much. Yes, it can be expanded, because like when you look at, I started from home testing a very small system. Now we went to the school, and now we are planning to go to the community. Then from there, we will think on how to expand more. But there's one limitation. That's why we are asking, are the UV system viable to low resource setting? Because still, we don't have UV system which are affordable for the communities, for the poor communities. Like in Kenya, we don't have. The system which are there is mercury lamps, and you have seen the challenges of the mercury lamps. And again, they're expensive. But again, the other issue is, even the system which we use in our community, we were given by one company. They were able to give us, and then we go also for testing. So again, we are worried, like, okay, are we going to sustain this? So those are just the main challenges which are there. But because of technology, what I'm looking at the top companies. Like in Canada, we have WaterSprint, and the USA, we have Acquisense. They're really working hard. And also we have Crystal IS, which are developing the UV LEDs themselves. There's lots going on. So I expect in the next few years, we can have big and cheaper systems, which now can go to low resource settings.
Yeah, we have another question from Mr. Garrett Pilgrim. Of course, colleagues, you can also unmute your mics and ask the questions. Feel free to do that, but some people may be shy. He asks, has there been any attempts to reduce or mitigate the source pollution of the river's spring water supply via improved sanitation, septic capture from the surrounding community, and use for household community biogas, thereby reducing the levels of contamination of water source and increasing the effectiveness of UV pilot community expansion?
Sure. Thank you for this. Thank you for, it's really amazing. I like to show this again to answer that into perspective. I think you can see still my slide, okay?
Yes.
It's unfortunate. This is what we have even at home. It's just unfortunate. You can see that is like the first one, the first service water. Here, 2 people died, and within the community, they got sick. And when some health workers came to test, they found it was contaminated with amoebic. They died, or they got sick from amoebic dysentery. And even up to now, there's no change which has taken place. So the water is still there. So, and we are thinking, okay, we can go and do something there. So you can see another one is a stream. It's not even a river, it's just a creek. And you can see even the color from, you say, like, this is not water which you can use for drinking. Animals go there, drink the water from there, from the source, because we are not far from the main source where the river is coming from. So they go there, and then it is destroyed. There's a lot of deforestation has taken place. Even this water, when I was young, the volume was huge, but nowadays it's like it's drying up. And then you see this one, which we are calling protected spring, that is now the one which the community says it's now good, like it's good for drinking. And you can see already this is not something which is good. Even if, like, and there's no any effort that has been made to ensure, like, there's no, like, destruction of the forests around, like everything is being destroyed left side, right and center. People are not getting that information, and like no person is coming in to really tell them this is what we need to do. And even if you tell them, there are so many issues that they're dealing with, and they wonder, like, already we have this water, we just drink. Yeah, so that is the issue. So for this effort, in terms of like effort to improve and also to prevent the pollution, like for the rivers already are polluted, and like so hard to go tell the community, oh, this one, because they saw animals passing through. So the only one which now is protected is the protected spring. That's like the one which you can really work close and then say, okay, we need to ensure this. That's where we are looking at, okay, how we can design a system which is now easier to protect, and you don't need to do so much to really force people to do that. But this is an effort which needs now a whole community to work on that. Yeah.
Valerie's asking her, are you looking for other areas you could put in your systems in other parts of the world?
Yes, thank you for that, Valerie. So as we speak now, we have plans to do projects still in Kenya. Not only that area, we are thinking about other locations within Kenya, and I'm also in talks with another country, which is in Tanzania. At the same time, we have indigenous communities. Even where I'm having this call from, in indigenous communities, so they have similar challenges, which we have also in the community I come from. So we are trying to see how can we apply also in these indigenous communities. So our aim is to look more in low resource setting and see how we can put this system to work for those low resource settings. Yes.
Well, yeah. Well, along those similar lines, what kind of support are you getting any traction with, say, the municipalities or the local governments in trying to assist with expanding that type of expansion?
Thank you for that. As for now, we haven't gotten any local government support or municipality or the national government because this is the first system. By the way, this UV system which we installed is the first which has been installed in Kenya. And now we are trying to see the result which we have obtained. Then we can talk to the local government because we have found the results. So with our results now, we can talk to them. We need to do this. And the next project which we want to do, we want now to combine the school and then the community. Then the government will be able to see, oh, this system which you have, it's able to serve either schools. It is a project which can also work in communities. Then we can easily attract the funding. But we are talking with people here and there to see how they can come in to support us in when we are doing this. And remember this is not just for also Kenya, it's not just for Canada. The aim, even as we are here, we are aiming to provide clean water to everyone. So that's the core thing. We may get even funding, then you do the project from your side. We do a project in Canada, we do a project in Kenya. It's all around. I think you understand the challenges, especially the low resource settings are experiencing in this. Yeah.
Okay, thank you for that. We have a question from Mr. Derwin Valley out of Trinidad. Go ahead, Derwin.
Hi, afternoon, everyone. Thanks, Mr. Jara. One quick question. How is the freshness of the water after you treated the UV? What material do you use in the storage tanks? You said, I think you ran through the presentation and you said, I think it doesn't last over a period of 20 days or something like that. Just to clarify, because I joined it late, just clarify on that. Was the maintenance process of the tanks, the storage tanks for the water, and how is the freshness of the water maintained as far as after the UV disinfection?
Yeah, thank you so much, Darwin, for that. It's really a very good comment or even question. Very good one, because that is whatever you've asked, it's really looking at the sustainability and the efficacy of that system and how to protect the community. It's not just putting a system there and then how are you going to maintain it? How are you going to sustain it? I think it's revolving around that. And that is the most crucial thing in the systems or projects which are done. Like if you overlook that one, then the systems or project will end up failing. So I hope you are able to see again my screen here.
Yes.
So what is happening, you can see here there is tanks and there's a big tank which is here. This tank is 10,000 liters. So this tank is just to collect the rainwater. Just to collect the rainwater and store. When it rains, it's just collecting the rainwater. So there is pipes which we have not shown there. They're behind this tank along the wall. So that is where we have we have a tap which we can use if we need to clean the tank. We will open that tap and then that water will get out. We can clean, like if we need to, anytime we need to clean, there's a tap which we all have. We need to open and then clean that given tank. And then even before that, we have a fast flush. If you look at the diagram, you still see there is pipes there, which is between these small tanks and then the big tank, you'll see a pipe running down. And then this is a fast flush. Like when it rains, before the water goes to the big tank, we must have fast flush to remove maybe this big particles and water view. And after the rain has stopped, someone has to go there open to empty that water so that to prepare for another rain which comes. So there's fast flush, and then even after that, the water goes to the tank. After some time, maybe dry season, we in this community we are able to know when it's raining. We can tell. So like if there was water which was remaining there, it's emptied and then the tank is cleaned. Now, after that, there's a water now, there's a tank which is behind, which I'll top there. There's two tanks up there. I had shown you here on this diagram, there's two tanks which are on the raised basement. So the first one is the filtration. So this filtration is the one which is removing all the particles and water view. And then the another tank which is labeled number 3, which we can see now here, the black one here, is just collecting the filtered water. And this tank should not be so huge, such that we don't need to store the water there for a long time. Because again, we may have some particles inside. It's just like to use for that day and that is it. And then collect overnight and then tomorrow again there's water because it is continuous. So we have to ensure this tank is not huge. The one which we need to ensure it is big and enough to collect the water is the first tank to have storage. And then after this, now the filtered water from this tank, the small tank, then it goes to the UV system, the UV system. Let me show you here, sorry for that. Yeah, this UV system, which is here. Now it goes here. So the water from now filtration, it goes to the tank, small tank around 500 liters. That's why we said 500 liters, but you can make it bigger the way you want. You look at the population. So the design you're making is according to the population which you have. And then it goes to the UV system. Then after UV system, immediately the water is collected here for use. So we don't store the water after UV treatment. It's just immediately after filtration, after the UV system or UV treatment, we use the water. So we don't have any issue like we need to store water after UV, no. And then the other issue to ensure the water quality is good even before the UV, that's where we are doing the biosand filtration. And then the other issue is the water in the main tank is not staying like for a whole month because we have a lot of rainfall and there is a continuous use. So the water is not stored there to wait like it will be used later. No, it's just a continuous use. So you'll find the water which rained within maybe 2-3 days, it has been used. And then the other water comes. So there's no long-term storage of this given water. So that is another thing. So in terms of maintenance, I've told you how we clean. And also the other filtration system, also we have, I'll show you also this diagram. There's so many valves which I designed and then installed. These valves I'll use also to do cleaning to ensure everything is okay. And then we have also this given pump which we have here is just automated so that nobody is going to tamper with the system. It's just the only thing you need to do is just to open the taps and then you get the water. I hope I've answered the question, Darwin, but we have to do still more. There's more things which still we have to keep thinking on how to improve very high efficiency of the system. But as per now, I'm still checking on the system. I have someone on the ground checking the system is working efficiently. Yes.
Oh yeah, Doctor, you did really well. One other question, and I know it's probably sci-fi thinking. I know you have different wavelengths to deal with different types of waterborne diseases.
Correct.
Is there any evidence of the organisms going past or there's a strain of organisms that doesn't respond to the wavelength or the current wavelength or the current accepted wavelength of the UV?
Okay, thank you so much. That's so good for that. Now that goes more scientific on that. I mentioned the different wavelengths of the UV. So what we have in this system, we are using, I hope, let me show you on that also to explain in perspective. Okay. Yeah, this is what we have. So the UV LEDs, we have different wavelengths, that's UVC, UVB, and UVA. So we have done lots of research in the lab, and nowadays we are not using UVB in water treatment. We are not normally focused on the UVC. So in this UVC, you can see where I have a graph here also, these ones. So the UVC system, which we are using in our project, is emitting around 275, 278, which we normally say plus minus 5, around 280. So it's revolving around 280. And the reason why we are using this wavelength around 280 is because it has two things. It can be able to affect or destroy the proteins, which you know it's responsible for infection and like to prevent you, like to cure where you are sick. Somehow it can help on that. And also it is absorbed by the DNA. The moment you affect or inactivate the DNA, then the microorganism is not able to reproduce. If you see 265, that is the optimum around which most of the microorganisms absorb the light, around the 265. But the challenge with the 265, it's not highly absorbed by the proteins. That's why we consider the 280. And now another factor which we consider is what we have in the market and what we have on the ground. I explained earlier on there is challenges of producing or fabricating the UV LEDs. I knew I'll get this question. One of the challenge is material quality. When you are adding aluminum, I explained that you are reducing the wavelength. So the lower the wavelength, the higher the aluminum you need to add. And the higher the aluminum you add, the poor quality the material you get. So you'll find two UV LEDs of 265 and 280. You'll find the 280 is more powerful than even the 265 in terms of power, So you find that the 280 even is performing so high. If you take two UV LEDs have at the same cost, you'll find 280 outperforms the 265 by far. And also the 265, I explained earlier on, some microorganisms, they can repair themselves. When they have been exposed to the 265, some of them repair as compared to the 280. To the 280, it like sometimes suppresses the repair of those microorganisms. So those are the things which we look at. And also the other thing is this, how do we really know like this UV system has killed most of the microorganisms? I think if you have done some of the research, you'll find this what we call MS2, bacteriophage. So this is like a standard microorganism. It's like a bacteriophage. It's a virus which eats bacteria. So this is the standard which is used to check how this UV system can be able to kill other microorganisms. So the inactivation of this MS2, if you are able to reach a certain percentage, let us say 99.99, you have killed the MS2. That means E. coli, you can destroy all of it, you don't find. And remember, MS2, the way it is used is because it is highly resistant to the UV. That is why it is used in the validation of the UV system. And therefore, when you take the UV system on the ground, you have tested it with this highly resistant microorganism before you take it on the ground. And then the other thing which you have to ensure and look up to is the flow rate of the system. What's the flow rate? Because if the water is flowing very fast, then the microorganism in the water, they have less time to absorb the UV light. So you have to ensure how you have designed the system itself and ensure what the power the system has. And then from there, you can know which type of system you need to use for that kind of water treatment. And therefore, from there, you'll be able to know, okay, if this UV system, it can kill MS2 at this rate, then this UV system has this power, this UV system has this flow rate, then you are very sure it will be able to perform its function. Yes.
Appreciate it really well. Thanks.
Thanks so much.
Well, right. I think we have really grilled Dr. Nyangarasi
Nyangarasi.
There's many questions, and we really appreciate your candor and how well you have presented this findings, your research findings as well to us. And we
Yeah,
really hope that you can be able to get more support for going
sure.
forward with actual implementation of these systems in the communities and in other places as well. So I'd like to thank you for this and thank all our participants for being so active in putting the questions. And of course, we'd like to thank the Operators Without Borders for making a good find again. And we hope we can have you back with us at some other point on some other matters related. But I think the salient matter here is that in the Caribbean, sometimes we think we do have challenges. And as we can see, you have so many more challenges and hurdles to clear. So I think it is a good eye opener, but also that we can see in ways that even through such fora that we can be able to communicate and perhaps partner with you in finding solutions for what you're seeking to do in achieving sustainable goal number 6. So that's really remarkable work. So we want to thank you for this. And of course, participants, that if it's Wednesday, it's CAWASA Wednesday webinar. And the next week, we will be looking again at the topic will be on the approach to dealing with water quality and health challenges ahead. And that will be presented by Dr. Weragoda. And again, we will be sending the notices around and that you can join us. Valerie, is there anything you would wish to add before we close?
No, there's just one thing in dealing with the innovation people at, I think we've talked with Joe Burgess, who runs the innovation lab for water utility in the UK. And this might be, if anybody is interested in doing a pilot project, they may be able to fund something. What they do is they fund innovation and new technology to see if it works. If it works and you use it, you pay it back, you pay them back. But if it's not something that's usable, then they absorb the cost. So if there is anybody out there who might be interested in looking at a pilot project and seeing if it would be useful in some of their rural areas, that might be something to look at.
Okay, also, we'd just like to pull a plug here again for CWWA and Operators Without Borders, who will be hosting a webinar tomorrow. I think that's 1:30 Eastern Caribbean time.
Yep.
Practical applications of incident command system for water utilities. So you can join this.
I've put the registration link in the chat.
In the link, so you can always join. Thank you. Have a good evening. I'm Ignatius Jean of the Caribbean Water and Sewage Association based in St. Lucia. Thanking you for joining us on CAWASA Wednesday webinar and looking forward to seeing you next week. Have a good one.
Good evening.
Good day.
Bye.
Thank you, Paul.